Okay, so this is our plan for today. I just wanted to talk briefly about one question on the test. Oh, and I also wanted to talk a little bit about the cited derivatives homework that you guys have been getting back. Because I put some comments on there and you want to make sure you take a look at those comments, but also I just wanted to talk a bit about how you're writing things and notation. In general, you're doing a good job with it, but I want to be clear about how we are writing and computing some things. So on the test, there was one question that some people missed, and that was the question involving the tangent line on the back page. And in that question, you're given a curve on a graph. Let's go ahead and get the graph here. And our graph is something like this, something like this. Right up here at 3, well, it kind of peaks at 2, and then starts bending downwards at 3. So, a little bit not quite so tall. There we go. And then it goes down like that. Okay. And what I asked you to do here is to simply sketch the tangent line. And almost everybody successfully sketched a line that was tangent to the graph, something like this. I wasn't too picky with it, but I wanted the line to be touch the wow. I wanted the line to touch the graph at this point and then have an appropriate slope. So that was one point. And then for the second point, I asked you what is the value of f prime of 3? And here, some people got confused about the difference between f and f prime. F is the value that is on the graph itself, and the reason I know that is really simple. It's labeled f of x. And so that means that f of 3 is in fact 6. That's the value right there. A whole lot of people told me this was f prime of 3, which it is not. What is our geometric interpretation of f prime? Slope of the tangent. That's exactly right. And so I need the slope of this line right here. We need to have that slope as something in the neighborhood of -1. I accepted any negative value between about a -0.5 and -2. So I just want to be clear about the difference between these two things because students will often get them confused. And Wednesday, when we look at graphs of f prime, I want to be really clear about those so that you do not get those confused. Are there any questions about the test? Okay. Well, let me take just a moment now to talk about how to justify your work on something like number 15 in your homework. And in number 15, you're given this function here, and you're told that it is not differentiable at x equals 0, and now they ask you why. If I'm going to diagnose points of non-differentiability, the diagnosis tool is going to be my cited derivatives. A graph is a good supplementary tool to get an idea of what the answer should be, but a graph is not going to be enough to justify any conclusions that you have about this point. In particular, when I look at the graph of y, what I find is that for x's that are less than 0, my graph looks like the graph of y equals 5x minus 1. And then when I look at the graph for x's, let me make this see. When I look at the graph for x's that are positive, then it looks like my graph looks like this right here. So looking at this graph, what does this appear to be in terms of points of non-differentiability? It appears to be a corner, right? This graph is not enough to justify that. Why not? because there is not a way to tell whether this is a corner or whether it is simply a curve that kind of smoothly turns in a very tight space. You see what I'm saying? So a graph is not enough. Instead, what I need to do is actually come and compute the derivatives from left and right at 0. And that's just a matter of doing limit definition. I'm going to take the limit as x goes to 0 from the left of 3x minus 2x, the values of x minus 1 minus f of 0. And same story here. But now this is where a number of people stalled out because they forgot what the absolute value of x is. Okay. So I have my setups here. Let me give myself enough space to evaluate them. There's this guy. And now the negative ones cancel. Here, I need to find some way to replace the absolute value of x with what it is. Keep in mind that my x's are all negative for this region. And when x is less than 0, the absolute value of x is the opposite of x. That's how we make this whole thing be positive, is by taking the opposite of a negative number. And therefore, I can replace the absolute value of x with the opposite of x, which gives me 3x plus 2x all over x is 5. Meanwhile, for x is greater than 0, the absolute value of x is simply itself. Also for x equals 0, but I don't care about that here. And so that gives me the limit as x goes to 0 on the right of 3x minus 2x all over x, which is 1. And now I have enough information to conclude corner, because my derivative from the right is 1, my derivative from the left is 5, and that nails it. Does that make sense to everybody? You look like you have a question. Okay. Okay. All right. Then let us talk about numeric derivatives. When I talk about numeric derivatives, what I'm talking about is estimating f prime of c using 2 points close to c. That's the spirit here. And specifically, we're going to use 2 points close to c to set up the difference quotient. Now, to help illustrate what I'm talking about, we're going to create for ourselves a typical kind of situation where this might occur. When I am estimating f prime of c, there are 2 main circumstances that I might wish to do that. The first is if I am confronted with a function that I don't have a derivative rule for and can't create using the limit definition. So if I have a function without a derivative rule, for whatever reason, short for function. And especially this occurs in the context of scientific data that have been collected. So functions that are represented by data points. And we're going to look at both of those today. In fact, I'm going to look at the second one first. With this problem, here's going to be our setup. water is draining out of a tank over the interval (0 to 7 minutes). Okay? And the height of water in the tank is modeled by a differentiable function h of t. Various values of h are given in the table below. Now, I haven't asked any questions yet. I've only presented some information, and I want. Okay. You're right. I did omit 4. I'll explain that in a second. Okay. Now, I haven't asked any questions yet. We don't even know what we're trying to find yet. All we have is a setup, an explanation of a situation. And I want to take some time to understand this. Usually we'll call this the stem of the question. And the stem of the question, the information given here in the stem of the question, would apply to all parts of the question. So I'm about to ask some questions A, B, and C, and the information that we have here is going to apply to all parts A, B, and C. Okay. Now I want you to observe some things about the language, and maybe you'll have some additional questions, because really what we're doing here today is in large part working on our translation skill, translating from English to math. So the first thing that I want you to observe is that the height has a label to it, and that label is h of t. So you want to think of h and height as being synonymous with each other. They aren't exactly. In real life, the height is whatever it is, and h of t is simply our model for it, our equation for it. So they're not exactly the same, but we're going to treat them as the same for this problem. Okay. That's the first thing. The second thing that I want you to observe is that our model is a differentiable model, meaning that the derivative exists for all points in the domain. So h prime of t exists for 0 to 7. Okay. Yes, sir. The stem of the question is all of the information that's given here. And then the actual questions are going to follow once we've gotten it. Okay. Because h prime of t exists, we can infer something about h. What do we know about h because h prime exists? If h prime of c exists, then h is continuous. That's right, and x equals c. So in this particular case, because h prime of t exists for all of these t's, that implies that h of t is continuous, and you as a problem solver need to be sharp enough to pick up on that fact. Does that make sense? Now, that helps us interpret the table a little bit. So I want to talk about how to read this table. And the first thing that I want you to observe is that we have labels for our variables, and we are going to have to use these labels in answering our questions. In particular, we have T labeled for time, and we have H labeled for height. And we also have unit labels, and these unit labels are the units that go with the problem, and every time I use an H, I want to put that unit label with it. So H of 1 is not 8.5, H of 1 is 8.5 meters. Does that make sense? Okay. The next thing I want you to observe that's really important is that these values that you see right here are not the only values that H has. They're the only ones that I know about. H actually has values for every t between 0 and 7. How do I know? Because it's continuous. H has values for every t between 0 and 7, but I don't know what the ones in the middle are. I don't know what H of 0.5 is. Although, because water is draining out, I would say that 9 is a better bet than 12. Do you understand what I'm saying? Because water is draining out, it's a good bet that H of 0.5 is less than H of 0. Because I'm losing water. Yeah. Yes, Jason, you have a question?
I was understanding that. Can we find like when t equals 0.002?
Yeah, we can't. We don't know what those heights are. We could estimate them in some way, but we can't actually find them. So if I were to estimate, I would want to estimate with a smooth curve. So if this is 10, and this is 0, and this is 7, what does it look like? It looks like my curve is headed towards 6, doesn't it? Right? So my curve looks something like this. Something like that. That's a nice smooth curve interpolation of my data points. Okay? But I don't know for sure that my curve looks like that. Does that make sense? Okay. That's the stem. We understand the setup now. We're being given some data points. We do notice that 4 got skipped, right? Probably that's because whoever's job it was to record the height at 4, they got distracted and forgot to record at 4. Or maybe water got on the paper and destroyed the data value. Who knows what happened to that data point. But you've done enough labs in science class. Yes? No? You've done enough labs in science class to know that data collection is never a perfect operation, right? Okay. So, now, here comes our first question. And watch the wording here. At what rate is water draining out of the tank at t equals 3 minutes? Let's make it t equals 2 minutes. At t equals 2 minutes. So this is our first question. Okay. Now, first of all, we need to translate the question into math. I need to know what math thing I'm trying to find here. And my eye is drawn to the fact that they're asking me about a rate at a specific time. How do we spell rate of change in calculus? Exactly, the derivative. I am looking for the instantaneous rate. How do I know instantaneous? Because they are asking for an instant in time. I'm looking for an instantaneous rate of change of the height of the water. And the name for the height in this problem is H. That's its name. Meters are the units. The name is H. And therefore the name for the rate of change of H is H prime. H prime of 2 specifically. So this is what I'm trying to find. Now, can't find this with derivative rules because I have no idea what the equation is that governs this function. Okay, fair enough. So the way I'm going to estimate this is to set up a difference quotient for points that are close to t equals 2. And I'm going to choose points on both sides of t equals 2 so that I get information about the function's rate of change from both times before 2 and times after 2. So that I'm going to estimate h prime of 2 as approximately h of 3 minus h of 1 all over 3 minus 1. Now what I'm doing, coming back to my curve, if you'll let me make the curve bigger. Here comes the h curve. What I'm doing is trying to find the slope of the line tangent at t equals 2. Sometimes I do that anymore. Tangent not really touch the curve. And the way that I'm going to do that is to pick a point as close as I can to 2 on this side and on that side, and I'm going to find the slope of that line. And if you look at that line, it looks pretty darn close to being parallel to the blue line, to the tangent line. So the slope of this secant line, which is the slope right here, is going to be an approximation to the slope of the tangent line in blue right there. And you can see that as long as my curve is pretty well behaved, that approximation is going to be pretty good. Yes, sir?
Well, that equation is a little different from instantaneous.
It is a little different from the instantaneous rate of change. What is it lacking? To make it instantaneous. What would I need in order to get some kind of limit? I would need a limit. That's exactly right. And that's the one thing I can't do with this numeric data. So I do the best that I can to evaluate the limit by evaluating from both sides the slope. Does that make sense? This is the best I can do with the information I'm given. Yes?
Can we calculate the rate of change between 1 and 2 and 2 and 3 so that you can approach from both sides?
Ah, yes you could. Here's the fun part. Suppose I got the difference quotient between 1 and 2. I'm going to take a quick detour on your question, and then I'm going to come back to this problem here. So what I'm about to say is in answer to Jennifer's question. If I computed the difference quotient, h of 3 minus h of, h of 2 minus h of 1 over 2 minus 1, that difference quotient would also compute a rate of change rate. And when I computed that rate of change, the best way to label that would be the derivative of h from the left at 2. And likewise, if I computed the derivative from the right, the best way to compute that would be this. Now here's the fun part. Because these two numerators have the same size, the best estimate for h prime would be the average of these two values.
So we would have to back to
Right, because when I average these two values, something miraculous occurs. The average of these two turns out to be exactly that. Yes. Yes. So actually, what I did was basically prepackage that whole idea and just captured it.
How do you find h prime of 3 and h prime of 1?
H prime of 3, well, we don't have to, because the question is asking me about t equals 2. I'll ask about some more points in just a minute to handle, because there are some issues that do come up. But for now, the problem is asking me about h prime of 2, and I'm going to set up h prime of 2 like this. Notice that when I did h prime of 2, I chose values that are close on either side. I call this the bracket method. To bracket something means to go around it. And what I'm doing here is bracketing t equals 2 in order to get my derivative. Okay, now I'm ready to plug in numbers. Notice that we go straight to an equal sign because I can actually plug in real values. This is going to give me 6.5 minus 8.5 meters. 6.5 minus 8.5 meters, and those units come straight from the table. All over, 3 minus 1 is 2 minutes, and those units come straight from the table too. Now let me pass on some friendly advice. And the advice is this. Everybody see how I set up the difference quotient right here? I have a large number of students every year who wish to skip this step and go straight to here. And they wish to skip it because they're in a real hurry and they figure this is going to save themselves like 10 seconds of time. Well, not. Okay, fine. But writing this helps focus your attention on two things. First of all, it helps focus your attention on the bracket. And second of all, it helps focus your attention on the fact that the numerator is the values here that are h, and the denominator is the values here that are t. And every year I have at least one student that gets this upside down because the t row is sitting there on the top. And so they want to put that in the numerator. And writing your difference quotient helps avoid those silly mistakes. So I'm just going to say, as a matter of friendly advice, write your difference quotient so that you can see what you're doing, so that the information comes out. Well, if I'm working on a test and I don't need to do anything else with this, then I'll just leave this. But today we're going to simplify it because we now need to take and interpret this right here. This is our analysis that gives us the value of h prime of 2, but I now need to interpret the meaning of h prime of 2 in terms of the question. And the interpretation is going to have three crucial elements to it. And the first is the use of English language to indicate the sign of my derivative here. What does it mean that my derivative is less than 0? What does that tell me about the water? Decreasing. Yeah, derivative is less than 0. It's decreasing. You probably had the right picture, Eli. You just said the opposite. Yeah. So we are going to use language to indicate that. Second, we're going to give the rate with its units. And third, we're going to be specific about what time we're talking about. So here's how this looks. We're going to interpret this by saying the water is, and here I'm going to use the language of the problem, the water is draining out the reason I use that language is that that's the language they provided to me. So that makes it easy. Whatever language they use, that's the language I use. At a rate of 1 meter per minute. This is the second thing. Notice what did I not put in my numeric rate? I did not put the negative sign. Why didn't I put the negative sign? Because I've already put it right here with the words draining out. Did I mess up the calculations? I get negative 2 over 2 is negative 1.
They're in charge at a rate of like 1 meter
Per minute.
like
Yes, and now we're specific. At t equals 2 minutes. So the three elements here are, first of all, I'm going to use language to indicate the sign. Second of all, I'm going to get the rate with units. And third, I'm going to be specific. Be specific. Because it is not true that water is draining out at a rate of 1 meter per minute. That would imply for the entire domain. And water is not draining out at a rate of 1 meter per minute for the entire problem. You can see that. You can see from here, it's pretty clear to see that the rate is decreasing as we go. In fact, it's almost 0 by the time we get to 7 minutes. Physically, why might that be? why would the water stop draining out at a height of 6?
I had less current, like pressure.
Sure, but that's a really sharp decline, right? I mean, over 2 minutes, we lose very little water. What's going on there? We had a couple of interesting answers in class, yeah. How did the water stop draining out?
The drinks on the bottom.
What? Yeah,
The drinks on the very bottom.
yeah, where does it look like the drain might be?
On the side, 16.
Like at about 6 meters, that's exactly right. That wasn't, when I constructed the problem, I wasn't even thinking of it. You and then Davon in my other class gave that answer. The other possibility is that the, whatever's draining out of it, like the hole, is getting clogged. Right? So, something is causing this rate to slow way, way down. Okay. Does everybody understand the 3 elements that are needed for this? Good. Well, let's look at a second question. It's going to look kind of similar. And that is question B. How quickly is water draining out from the tank at t equals 4 minutes? Now, this problem offers a couple of variations on what we did previously. First of all, notice the language here, how quickly. How quickly is a synonym for at what rate. So our original problem here had at what rate is water draining out. How quickly is water draining out? Same question. And the answer to that question is going to be h prime at what time? At time 4. So the first little wrinkle with this problem was simply that we needed to be able to translate the language. The second wrinkle that's kind of interesting is this. When I go back to my table, look what isn't there. Yeah? Is that a problem? No. What am I going to do, Tommy?
H prime of 5 minus H prime of 3 over 5 minus 3.
Almost. Not h prime, but h. I'm estimating my derivative with a difference quotient with values from h. So I'm looking at a change in h over a change in time. Does that make sense? And that's exactly what I did for the previous one also. Okay. H prime of 5 minus h prime of 3 over 5 minus 3 would actually compute h double prime. Okay, and now I'm ready to plug in values. Let's see here. Clara, give me values.
16 minus 16
Oh, I was really hoping you would do what you needed to do. What did you miss? The units. Oh, every time. What are the units that go with the 6.5 and the 6.3? Not there. Now this is right. Here we do the computation, and we get negative 0.1 meters per minute. And now we're ready for the interpretation thereof. Jason, how do I interpret this?
Water is draining at a rate 0.1 meter per
Perfect. Let's go with t equals 4 minutes. Yep, very good. Yes, sir.
Cancel.
Yeah.
Let's see which one. For t equals 2, can we just divide from 8.5 to 7.0 plus 6.5 minus 5.0. And you said it's average of 5.
Right. Watch what happens if you do that. You would get, our first rate would be 7.0 minus 8.5. Final minus initial. And our next one would be 6.5 minus 7. Look what cancels. So that what you get is 6.5 minus 8.5. And all of that is over the total 2-minute time interval that you had right there. So averaging left and right for equal time intervals will give you the same thing as doing the bracket between them. So just do the bracket.
So that means every time we get 2 or 3 on
That's right. So that doesn't actually always happen. Like these deltas may have been different. Like if I asked you for h prime of 3, you would have 1 on this side and 2 on this side. But bracketing gives extra weight to this side, which is appropriate because that goes out further in time. So I actually would really want you to do the bracketing each time. There's underlying stuff. When you take a course in numerical analysis, then they'll go into greater detail about error and such. Yes.
So for the ladder B question, we got the h prime of 4.
Mhm.
Can we get h of 4 by this?
We could estimate h of 4,
So
but we would not be able to get an exact value. Yeah. But we could use this rate to estimate h of 4. In fact, it's probably what you think it is. It's going to be 6.4 as our estimate by averaging. But we could use this to also estimate like h of 3.7, which you couldn't do with averaging, right?
in case they don't ask what is the rate of water draining out at x equals 3, at t equals 3.
Oh, I see. So you'd want to then take that value and turn that into additional information for your derivative. You can do that. When you do, it's hard to keep track of which values are real data values and which values are ones that you have generated. But that kind of process is actually done in statistical analysis. It's called infilling. And it's useful, and it's also really dangerous because you can fool yourself. You can see why. All right, so our last question on this problem is going to be, how quickly is water initially draining from the tank? Okay. Now, we see some elements that we have seen before. How quickly is a synonym for what math thing? What rate, which is math derivative h prime. But, strangely, they don't tell us what time they're looking for, or do they? What word do we see here? What does that mean?
At 0.
At t equals 0. Initially means at the start. So they're asking me for h prime of 0. You okay? Yes,
Initially is right.
at the start, when t equals 0. Okay. Now, here's the second little thing that's kind of unusual. And that is that when I go to t equals 0, I don't have anything to the left. No information whatsoever on the left. So I'm going to handle this by going only to the right and using that as my left flank right there. Now when I do, I have a choice of ways to label this. Either I can label this as h prime of 0, or more specifically, I could label it as h prime from the right at 0. I prefer this labeling because it is more precise in terms of what I'm doing. But it is also the case that the analysts at the endpoints of domains will take the derivative to be the derivative from the appropriate side. And so we write this as h of 1 minus h of 0 all over 1 minus 0. And we pull in values, 8.5 and 10. Meters, 1 minus minutes. So it gives us negative 1.5 meters per minute. And now we're ready for a translation. Tony, you're on.
Initial rate of drinking of water is of magnitude 1.5 meter.
Oh.
Negative, it's already been taken care of.
1.5 meter per minute at cube.
We've already said that too. This is being specific. This is a little awkward English-wise, so this is correct and everybody would understand it. But a native speaker would say, water initially drains at a rate of 1.5 liters per minute. Does that make sense? So we have the adverb of time right here. Water initially drains. Good? Okay. Very briefly, we're going to leave this problem and look at a function that we don't have a derivative rule for yet. If f of x equals e to the x, what is f prime of 2? Now, at first, this question looks nothing like the previous question, but actually it's really the same. Because I do not have a derivative rule for this, and so I'm going to estimate the derivative by picking two values that are close to 2 on either side of 2. And what are the two values that I can pick that are closest to 2 using my 4 decimal place standard? Exactly. And what's the one on the other side? Exactly. Oop, there we go. There it is. That's my estimate. Now, when I actually compute this, I'm going to need to compute it on a calculator. And it's a really straightforward computation. In fact, you see it here from the previous class. When I compute this, I'm going to compute it as e to the 2.0001 minus e to the 1.9999 over 2.0001 minus 1.9999, all at once. And when I hit enter, whoop, I get a value for the derivative, 7.3891. And if I want to check that, then I can let y equal e to the x and use second calc dy dx to find the derivative at x equals 2. And lo and behold, it gives me the same value, 7.3891, which is really nice. Yeah. The secret, by the way, is that when the calculator does derivatives, it does exactly what we just did here, except instead of using 4 decimal places, it uses 5. So it goes 2.00001 and 1.99999.
Can I see it?
Yeah, and I'll also post this video.